Injection molded parts at home would be awesome, but that would mean buying special equipment. Sending prints out to be professionally made is another good option, but again, that's extra cost and possibly takes weeks to wait. So is there another way to make the strongest 3D prints at home without buying anything extra? Well, I think there might be, so I think we should give it a try. So stick around. A while back, I tried to soften and bend a 3D printed PETG part in a mold that I made, and it worked. But it wasn't stronger. In fact, it became pretty brittle. My main mistakes were that it wasn't completely solid, and my heating process consisted of blasting it with a heat gun to an unknown temperature and cooling it quickly. PETG can be pretty tough, but apparently not when using this heating process. It also does really well when printed completely solid with fairly thin walls. But I think we can do a little better. I think I have just the thing for our test subject. I've lost or broken most of these. The originals are injection molded glass fiber reinforced, and if I were to 3D print them, they would be pretty weak. So I'm going to copy it to be as close to the same as I can get it. These injection molded parts have these very slight draft angles, so they release from the mold easily. So I will make sure to add those in too. So next I need to add a mold to go around that part. Now that mold is strange because on the cylinder side it covers half of the part exactly, but where it meets the clamping head, it changes and shifts over to this face, which is set at a very slight angle as well. I've added in clamping holes through half of the mold and into the other as well, and I've also added in tapered alignment pins too. I need a mold which can resist far higher temperatures than the material that we're trying to make stronger, so I'm using PPS carbon fiber and printing it on my GD Plus 4. And since I want to use this mold over and over again, I'm going to be printing it 100% solid as well. The first model that I printed had the chamber set to 55 degrees Celsius, but that was not quite hot enough. These solid parts are really prone to warpage, so the number that worked best was 65 degrees Celsius. Aside from the warpage on one of the parts that I decided to reuse, the mold looks really good. The tough part is that we need to get plastic into this mold without actually injecting it. So what I've done is taken the original part and I've offset each of the faces in a little bit by 0.15 millimeters in order to account for any variance in my print size. Now that's because I'm printing solid. If I were to print this with infill, it would be a little bit easier to control the overall size, but printed completely solid usually ends up with a little bit too large of a part. It doesn't seem like it's that much, and I'd probably be able to hammer it in, but I would rather be able to slip the parts together instead. In the bamboo, I have some PETG carbon fiber printing. This is bamboo filament, red brick carbon fiber. And inside the GD Plus 4, I have purple ABS glass fiber 25 printing. And I have some GD PLA carbon fiber printing on the X1C as well. Next, I need to add the heat set inserts into the mold, and I'm using 10 millimeter long brass heat set inserts. These are for M3. So I'm going to start with the lowest temperature and maybe the easiest, hopefully the easiest first. Now these are still snug in here, so what I'm going to do is spray the inside of this mold with some silicone spray, and that should also help as a release agent. And I'll do the exact same for this one. We'll slip this in, and I'll probably need to use my vise on my workbench here to clamp these tight together. And then I can use the screws to keep it tight. It's time to bake this, and because this is PLA, I'm going to do this at 150 degrees Celsius, so it's below the extruding temperature of what you'd have in your 3D printer, but well above the softening temperature of this plastic. So we should get a pretty solid part by the time it's done. I don't know whether I'll be able to easily remove it from the mold. We'll have to find that out later, but there are some areas that we can knock that out if we need to. Let's go ahead and get this into the oven. Okay, so I want to mention that this is completely experimental. The spray that I've used really is not the ideal spray. So what I'm going to do is make sure that my shop remains well ventilated while I'm running this. So I'm going to set it to 150 Celsius, 300 degrees Fahrenheit or so. And I will do 2 hours. And that should give it plenty of time to get warm right to the center of this model. And we'll do the holes pointed up. It is the next morning. Let's open this up. It should have completely cooled by now. And now we need to see if we can actually get this thing out of here. The mold still looks good. That's a good sign. And normally when you anneal a 3D print, it will shrink a little bit, so we might have a chance of easily getting this thing out of there. But on the other hand, this surface of this material is a little bit rough, and I'm not sure how easy it is going to be to overcome that. So let's go ahead and open this up, or try and open it up and see if we can get this thing apart. Interesting. Well, that's not a good sign. These little pins came off in there. It does look like it remelted though. Look how it actually flowed out into here. That does look like a completely solid part. It even has the parting lines in there. We had some issues. Unfortunately, I lost some of the pins in here. So I don't think I can reuse this one, but luckily I had already printed another cap as a replacement, so I can definitely do this test again with another material. I'll try and dig these out of here, but it really isn't that important. What is important is, if you can see here, we have some flash that started to come out in the seams, just like you'd have on an injection molded part. So that is definitely a good sign. I was having a hard time getting those little pieces out, so what I did is drilled a hole from the back side, and I used this thin punch to punch them out. The problem was, while I did that, it put quite a bit of pressure on it, and it created this little fracture line right here. Very, very small. So that's not a good sign. The real test will come in a little bit when we test how strong these are, especially in this area here where this is going to be really prone to breaking. So I'm going to go ahead and do the other ones, but before I do, I'm going to adjust the mold a little bit. This one had some holes in the bottom, which allowed me to knock it out really easily, but this one didn't. So what I'll do is drill a hole, and then I will tap it and add a screw in there, and that's going to work as a temporary plug. I'm going to go through the exact same process with the PETG carbon fiber, and if that one works, I will do the exact same thing with the ABS. Each one I will be incrementally increasing the temperature of the oven. So for PETG carbon fiber, I'll be using 160 degrees Celsius, and for the ABS, if that one works, I will be using 180 degrees Celsius. I wasn't sure how safe this was to do inside, so I decided to do the other ones outside. And I noticed something really strange with the PETG carbon fiber. Take a look at this. It's all bubbled up outside of the mold. So, not sure how well this one is going to turn out. Well, there's no question now in my mind that it was able to completely remelt what was inside, but I didn't expect it to come right up through the mold. If I had known it was going to do that, I probably would have done the same tapping and put some more screws in here as well, just to prevent that from happening. I don't know whether it would have built up a lot of pressure in there. So let's see if we can open this thing up and see what it looks like inside. I don't have high hopes for this one. Well, this mold may be ruined. I haven't been able to get this out even by punching all 3 of these holes, and this is not a good sign with PETG, but you can see inside it's hollow. So either it's had a reaction with the silicone that I sprayed on there, or maybe it is expanding because there was moisture inside when it was heated up, which shouldn't be the case because these parts were just printed. I don't have enough PPS carbon fiber to reprint the mold, and even though it was interesting to test, it is far from worth the time, cost of materials, and the hassle to try and remove the parts as well. The smoothness of the mold was a problem, the weakness of the layer lines on the sections meant to create the hollows, and maybe the release agent was a problem also. The biggest surprise was the PETG expanding like it did and creating these big hollows inside. I did not think that that would happen at all. I'm really curious why the PETG carbon fiber expanded so much, so I'm going to pop these into the oven and bake them to see what happens. The print on the left is coated with silicone spray, the one on the right is not. Now let's see if there's a difference. So there is quite a bit of a difference, not just in the size, the overall size is different, but the texture. If you look at the surface texture, it's much more rough than this one is. And on the bottom, it's pretty flat, pretty uniform, no air bubbles. And on this one, there are some bubbles, and there's this depression in here as well. So I think the PETG and silicone has reacted to cause this one to get larger, to expand, and have all of these air bubbles in it. But it did produce this really unique shape, either a creepy alien or Devil Scooby-Doo. Well, we did have some success on the PLA carbon fiber, so let's go ahead and test those. I have the 3D printed part, which has not been reheated, and then I have the reheated versions. So I can put these in the vise, and I have my crane scale as well. And what I'll do is I'll pull on these tabs and see how much of a difference there is. There is an improvement, and we can also see that the position of the break point changed to a little bit lower down, really where you would expect it to be if it is not a 3D printed part. So that's good. So I can't say that I would try this again, but what I would do instead is redesign the clamps to take advantage of the strengths of 3D printing. The original was designed to use as little material as possible. Now we only need to worry about the strength. So let's redesign one that is a fully 3D printable replacement that is strong. First, I'll remove what I don't need. Those recesses in the column need to go. I'll remove the ones on the top section as well for now while I make some adjustments. We need to lay this part fairly flat, and what we can do is remove material on an angle, and that way we'll have a perfect base to start out with. The flexible fingers that extend are useful when the workmate is being stored, and also I like to insert them in from below so that I can keep them on the bench, but then I have a completely flat surface to work with. So I need to extend the fingers down so that they meet that angle as well. Next, I'll bring the cylinder bottom down by 3 millimeters to create a circular cutout, and that will create a far more gradual and stronger transition. I'll add some chamfers and fillets, and that'll clean up any sharp corners as well. I don't like the sharp transition between the column and the top of the clamp, so I will slice them apart first, then I will add an unequal sized chamfer and then rejoin them. This will allow me to add a radius where both of the parts meet, which won't impede the final seating position of the clamp. Now I'll add some recesses back into the top, leaving more material than the original design had. A few chamfers to remove the sharp edges just for fun, and I'll add a little 3D printed spring at the bottom. This will help to prevent these parts from breaking off like the originals had been, and it's also just a cool thing to do. I'll print these in PLA and give them a try. and these work great. They should probably be something less wood colored for the final batch, and I've made these available for download for free in the link below if anyone happens to need a replacement for their Black & Decker workmate. Let's go ahead and break this one as well and see how much stronger this one is. That took quite a bit more force than the PLA version. Pretty impressive for PLA carbon fiber. When I have some more high temperature filament, I will give ABS a try for fun, but realistically for the cost and the time involved in making a mold like this, it is far better to redesign the model to make it really easy to FDM 3D print. I could have made the test prints simple cylinders, but that's not a realistic example. I wanted something I could actually use as the test, and it was an interesting experiment, but in the end, this was a failed attempt at making stronger parts. Thank you to each of my patrons for helping to support this channel and for making these videos possible. And if you'd like to help as well, there is a link down there below. If you want to help support this channel in a different way, I have a short list of products that I use in my shop on a regular basis, and those links are down below as well. Take care, and we will see you on the next one.